Hello everyone, this is Eshaan, EC Part 2, and today I'm going to discuss with you recursion and binary exponentiation. Now before starting off, I would like to recommend you to have this doc opened on some other device so that you can access it as and when required. And before defining recursion, you must know what a function is. A function is a set of statements which has to perform a particular operation. Functions greatly reduce the length of your codes as instead of coding the same lines again and again, you just make multiple function calls, and this would take relatively less space and less time to code, so you can submit your code faster. Remember, speed matters a lot. Now, as far as the basic syntax of a function is concerned, it consists of a function name, which may be anything, but it is recommended to name your function according to the task it performs. Like for multiplication, you can name it product, for addition, you can name it sum. A function also consists of a parameter list, which may be empty. Now, these parameter lists is basically a list of the operands on which the function operates. Like here in this case, it consists of two integers x and y, and the product function simply takes the product of them. Now each function has some return value, which may be null in case the function is not returning anything, which may be an integer, which may be a decimal, which may be any compound data type that you can make using structs. Now coming on to recursion, recursion is an instance when a function calls itself. Like in the definition, you will see the function calling itself. Now what does a function call means? A function call is basically an order given to the function to perform the task for which it has been defined. Now you will understand it more clearly once I give you a few examples of recursion. Now, before going on to the examples, you must know that each recursive function must have a terminating condition. Now, what is this terminating condition? By terminating condition, it is a condition through which we bring the function to an end, because the function keeps on calling itself repeatedly. If there is no end, the function would keep on calling itself and it would fall into an infinite loop. And so you won't be getting the desired verdicts. Instead, you might be getting time limit exceeded or something like that. Now, basic examples of recursion include the Fibonacci series, which you are well aware, and also the factorial. You are aware of both of them. Now, coming on to the implementation of the Fibonacci function. Now, here the return data type of the Fibonacci function is int, because the final answer that it is going to return would basically be some integer, or we can even use a long int over here so as to extend its range. Now Fibonacci is the function name and n is the input, like we'll be calculating the nth Fibonacci term. Now coming on to the terminating conditions, we know that the 0th Fibonacci term is 0 and the first Fibonacci term is 1. So as and when we encounter 0 or 1, we return these values. Else we return Fibonacci of n minus 1 plus Fibonacci of n minus 2. That is the sum of n minus 1th term of the series and the sum of the n minus 2th term of the series. Now this is very much straightforward according to the definition of the Fibonacci series. Now time complexity of recursive functions. You might be aware of time complexity. If not, time complexity is basically the runtime analysis of your code. Basically, it is about the execution execution time that your code takes. It might be we usually express the time complexity of a code in terms of the input. It may be O of n, like order of n square, or something like that. Now, when we analyze the recursive functions, let's take the example of the factorial function. Now, we have defined the terminating conditions, because we know that factorial of 1 and factorial of 0 both return 1. Else, we return n into factorial of n minus 1, which is very simple according to definition. Now, this recursive function makes n calls. Now, why n calls? Like we'll be calling factorial of n. Now, this factorial of n calls factorial of n minus 1. Factorial of n minus 1 is going to call factorial of n minus 2, and this goes on till you reach 1. So overall we'll be making n calls and during each call we'll be performing a multiplication operation. Now multiplication operation is a constant time operation. It takes O of 1 time, okay, order of 1. So the total time complexity of factorial function is going to be the number of function calls into the work done in each function call. So the total time it would take is n into O of 1, which is O of n. Now for the Fibonacci function, it is going to take a lot much time, as you might have observed that when you call, no, I'll be using f of n for the Fibonacci function for simplicity. Now when you call, when you take the example of n is equals to 5, now it is going to call f of 4 and f of 3. Now f of 4 is again going to call f of 3 and f of 2. Okay, and f of 3 is again going to call f of 2 and f of 1. You might see in this tree that f of 3 is being called twice, f of 2 is being called thrice. For larger n, the results for smaller inputs are going to be called multiple times. Therefore, the Fibonacci recursive function takes exponential time. It is somewhat of the order of 2 raised to power n. Now, these recursive functions find its use in many other functions. Like you will be studying about depth first search, which is a graph algorithm. It has both an iterative and a recursive function. And recursion is also used in binary and matrix exponentiation. Binary exponentiation. I'm going to teach you right now. And also, while coding recursive DP solutions, DP is dynamic programming, which you are going to study later. Coming on to binary exponentiation, first take a look at calculating a raised to power b. Now the naive approach would be to multiply a b times. Now coming on to the time complexity, we'll be performing b multiplication operations, and each multiplication operation takes constant time, that is O of 1. So overall we will be having a time complexity of O of b. Now this is good when b is quite small. Now for what about larger b's? Like what if b is of the order of 10 raised to power 18? And believe me guys, you will be seeing inputs like these quite a lot. So and if we calculate 8 raised to power b with this algorithm, this is definitely going to give us the verdict time limit exceeded. So what are we going to do? How are we going to optimize this time complexity? This is done by binary exponentiation. Binary exponentiation performs the operation a raised to power b for very large b in a time complexity of O log of b. When I say O log of b, the base of logarithm is 2. It is calculated with base 2. So what binary exponentiation actually does? First, we convert b into its binary representation. Now what does the binary representation of a number mean? We keep on dividing a number by 2 and we keep a track of its remainders, and we just print the remainders in the reverse order. Like while calculating the binary representation of 11, we first divide it by 2, the quotient comes out to be 5 and remainder is 1. We again divide it by 5, we again divided by 2, I'm sorry. The quotient comes out to be 2 and we get a remainder 1. We again divided by 2. This time we get no remainder and 1 as the quotient. We again divided by 2, 0 as the quotient and 1 as the remainder. Once you achieve 0, we stop dividing and we put these remainders in the reverse order in order to get the binary representation of a number. Okay. Now what does the binary representation of a number represent? Now let's index this binary representation starting from the right. This is the 0th index, this is the first index, this is the second index, and this is the third index. Then we can write that 11 is the 2 raised to power 3 into 1. See, at the third position we have 1. Now coming on to the second position, we don't have 1, we have a 0. So we write 2 square into 0. Then going on to the first position, 2 raised to power 1 into 1, and to the last position or the 0th index, we get 2 raised to power 0 into 1. So this is the binary representation of 11. Um, Now, how are we going to optimize the time complexity? Just a second. Now, since we have already converted the number b into its binary form, so what we are going to do, let me just come to the implementation part first, then I'll be explaining the algorithm to you later. The binary exponentiation has two implementations, a recursive implementation and an iterative implementation. Iterative means using loops. So this part is the recursive implementation. You see that the function binpow calls itself, and there is a terminating condition as well when b is 0. Now the following one is the iterative implementation. Now let me explain the implementation to you in a bit detail. Now let's calculate 3 raised to power 11. Now 3 raised to power 11 can also be written as 3 raised to power 1 into 2 cube plus 0 into 2 square plus 1 into 2 raised to power 1 plus 1 into 2 raised to power 0. And using the properties of exponents, we can write it as 3 raised to power 8 into 3 square into 3 raised to power 1. Now, what does the implementation say? Look to your left onto my VS Code setup, where the binpow function has been defined. Now, let us call the function for 3 and 11, where A is 3 and B is 11. So, if B is 0, we straight away return 1, else we call the function again and calculate a value result or res, which is binpow a comma b by 2, or in our case a is 3 and b by 2 would be 5. Remember, while dividing, in case there is a remainder, we scale it down, we take the floor of the quotient, we take the floor as the quotient. So let us represent binpow function as bp. So first we will be calling bp of 3 comma 11. All right, now since 11, which is rb, is not equal to 0, so we will be calculating the value of res by again calling the function bp with 3 comma 11 by 2. All right, now 11 by 2 is 5. Now you know that 5 is again not 0, so again we calculate some res, which is bp of 3 comma 5 by 2. Now 5 by 2 would again be 2. Now 2 is again not 0, so again a recursive wall would be made, and we will be calculating res pp of 3 comma 2 by 2, which is 1. Again 1 is not equal to 0, we would be calculating res as bp of 3 comma 1 by 2. Now 1 by 2 is 0. Now the terminating condition says that when b is equals to 0, we return 1. That is, the value res is equals to 1 is stored when we call bp of 3 comma 0. Now bp of 3 comma 0 would be called by bp of 3 comma 1. You can see it like this, like when a would be 3 and b would be 1, since b is not 0, we'll be going on to here where long res is written. Long res is equals to sorry, just a second. Long res is binpow a comma b by 2. Now a is 3 and b is 1, so 1 by 2 would be 0, and we'll be basically calling bin power 3 comma 0, and we know that bin power of 3 comma 0 is 1. So here the value of res is 1. Now going on further into into the definition of the function, if b percentile 2 is non-zero. Now this if b percentile 2 simply means if b percentile 2 is non-zero, this is basically equal to this, we return result into a. Now our result is 1 into 3. So basically we will be returning the value 3. All right. This function would be returning 1 into 3. So the new value stored in result would be 3. Now you again see that bin power of 3 comma 1 would be called by bin power of 3 comma 2, because suppose suppose a is 3 and b is 2. Since b is not equal to 0, we will be going to long rest again. Long rest is equals to bin power of 3 comma 2 by 2, which is 1, and we know that bin power 3 comma 1 we already calculated, it is 3. So the new value calculated of result is 3. Now since b is equals to 2 and b percentile 2 is not 1, b percentile 2 is basically the remainder that is left by dividing b by 2. Since b percentile 2 or b modulo 2 rather, b modulo 2 is not 1, so we return the value res into res. Now res is equals to 3 and res into res would be 9. So BP of 3 comma 2 would be 3 into 3, that is 9. Now you can actually see that BP of 3 comma 2, which is 3 raised to power 2, is 9. BP of 3 comma 1, which is 3 raised to power 1, which is actually 3. So in other ways, we are calculating the values of the steps which actually match our results, which actually match the actual results which we'll be calculating by the naive implementation. So the new value stored in res would be 9. Now you may see that by the same explanation, BP of 3 comma 2 would be called by BP of 3 comma 5. Now in case of 5, B percentile 2 is again 1. So we will be returning res into A, which is 9 into 3, which is 243 or 3 raised to power 5, which is very true as 3 raised to power 5 is 243. Now BP of 3 comma 5 was called by 3 comma 11. Now so the value stored in result is now 243, and since 11 percentile 2 or 11 modulo 2 is 1, we will again be returning rest of 243 into 243 into 3, that is 243 is 3 raised to power 5 into 3 raised to power 5 into 3. All right, now if you simplify this a bit, this changes to 3 raised to power 8 into 3 raised to power 2 into 3 raised to power 1, which was that we wanted to calculate. Now why this code takes log of b time? Because we are again and again dividing b by 2. So overall the maximum number of terms, maximum number of distinct function calls that we are going to make is log of b. That is why the runtime, that is the time complexity of this code is log of b. Now you can very well see it here as well. Now when we call bin power of 3 comma 11, since 11 is not equal to 0, bin power of 3 comma 11 recursively calls bin power of 3 comma 5. 5 is not equal to 0, bin power of 3 comma 5 recursively calls bin power of 3 comma 2. This again calls bin power of 3 comma 1, and this again calls bin power of 3 comma 0. Now here we reach the condition when b is equals to 0, so a value res is equals to 1, that is the base case value, is stored. Now and this value is returned to bin power of 3 comma 1. Now as 1 percentile 2 or 1 modulo 2 is 1, we change res to res into a, that is 1 into 3, and a new value of 3 is stored, which is the value returned by bin power of 3 comma 1. Now this value is given to bin power of 3 comma 2, as you can see by the arrows. Now 2 percentile 2 is not equal to 1, so we simply return now so result is changed to result into the previous result in result square, that is 3 into 3 is 9. So bin power of 3 comma 2 returns 9 to bin power of 3 comma 5. Now 5 percentile 2 is again 1, so it returns res into a, which is 9 into 9 into 3 or 243 to bin power of 3 comma 11. Now as 11 percentile 2 is 1, we finally change the output to res into a, that is 243 into 243 into 3, which is 177147 or 3 raised to power 11. The iterative implementation is also quite simple to understand. Now here we simply loop over b, and we keep on dividing it by 2 such that until it is greater than 0, and we perform the same operations that we actually performed recursively but using a loop. Let's see the iterative implementation as well. Now it says that long that is the same long int bin pow, long int a, long int b are the function parameters. Now initially we initialize result to 1. Now while b is greater than 0, if b modulo 2 is 1, we multiply a into the result, and each time we square up the a that we obtained earlier, and we divide b by 2. So what are we actually doing is, now while b is greater than 0, now b is initially 11 and 11 is greater than 0. So since 11 is greater than 0 and 11 percentile 2 or 11 modulo 2 is actually 1, so what we do is we multiply into the result the value a. Result was initially 1, so result now changes to 1 into 3, which is 3, and we square up a, so a becomes 9, and we divide b by 2, so b becomes 5. Alright, now since 5 is still greater than 0, we check 5 percentile 2. Now 5 percentile 2 is again 1. So we multiply res with a. Now a has changed to 9, so res would be 3 into 9, that is 27. Let me use another marker, and we square up a every time, so a now becomes 81, and we scale down b as well, so b now becomes 2. Now see that 2 percentile 2 is not equal to 1. So we won't be making any changes to result this time. We simply would square up a. A would become 81 into 81, that is 6561, and b would again be divided by 2, and it is going to become 1. Alright, now 1 percentile 2 is again 1, so this time we are going to multiply the result with a. Remember a has changed to 6561, and we had 27 in the result, so this gives us 27 into 6561, and b is now again divided by 2, and this becomes 0 and breaks out of the loop. Now 27 into 6561 is 177147, that is the value we required. Now if you notice carefully, res becomes 3, which is 3 raised to power 1, then it becomes 27, which is 3 raised to power 1 into 3 square, and finally it becomes this 3 raised to power 1 into 3 square into 6561, which is 3 raised to power 8. If you remember, this was what we calculated. We wanted to calculate it. We wrote 3 raised to power 11 in terms of the binary form of 11, and it came out to be 3 raised to power 1 into 3 square into 3 raised to power 8. So this is actually the definition of the iterative version, and its time complexity is same as that of the recursive version only. Both are O of log b. Coming on to the doc again. Now, calculating a raised to power b modulo m. Now, calculating a raised to power b modulo m basically means printing out the remainder when a raised to power b is divided by m. Now, now sometimes a raised to power b is so large that it does not fit in the range of even 64-bit integers, which is the largest data type that C++ provides. In these cases, we are asked to print the remainder on dividing it by some integer m so as to avoid overflows. Okay. Now, two of the most basic properties of modulo or the remainder operator are these: that a plus b modulo c is a modulo c plus b modulo c overall modulo c, and a into b modulo c is a modulo c into b modulo c overall modulo c. Now, these are quite easy to see. You can just take basic examples like a is equals to 5, b is equals to 3, and c is equals to 2, and you can easily see that these properties actually hold true. And these properties are very much used when you actually solve the combinatorics problems. That are combinatorics is basically PNC, and there, since the output is always quite large, so you are actually asked to print the output via modulo something, and there you use these properties. So this is actually a varied implementation of binary exponentiation, where we print the output modulo some integer m. Just two changes are made. Wherever we multiply rest with a, we take the remainder with m, and wherever we multiply a with a, we take the remainder with m. So this sums up binary exponentiation. Here are some sample tasks which you can try. The first four are the this problem recursion 1385D is quite good. CSCS problem, you can also try this CSCS problem, which is straightforward binary exponentiation only. Also, these four problems involve some bit of PNC as well, and but you will see that you will be needing binary exponentiation in them. For more resources, you can check out this link as well. Thank you.